I'm very sorry for the technical difficulty. Just before I came in, actually I used it and it was working fine, but here, but I think now we are back, so that's good. Yeah, my name is Fitsum Tariku. I'm the director of the Building Science Center of Excellence. And before my kind of short presentation, I'll give you what we do at the center. Basically, the Building Science Center of Excellence, we try to do improve buildings so that we make them high performance. When you say high performance, we'll be looking at the energy performance of the buildings, the durability of the building, and thermal comfort, and also integration of sustainable building materials into building designs and our applications. For that, we do some research on materials. So in materials, we do insulation material, for example. Like in our houses, we have traditional insulation material, fiberglass. In 1 inch, you get R4. But now with a new material, with vacuum insulated panel, you get R40. So that's like 10 times. That means your wall can shrink to 1/10 of thickness. Or there will be additional different kind of materials coming to the market. So we'll be doing the research on those kind of materials and how they could be integrated into buildings. So in only performance in one aspect may not be good enough. It might be good for energy, but it might have an impact on durability or indoor air quality. So we have to be looking at from all sides. So you will see here a sustainable building material research. We are trying to use natural-based fiber materials to create insulation materials and integration into building envelope. And here is aerogel material. Again, it's highly insulated materials. So our research starts from the materials, and then we move into the envelope. So okay. Yeah, so from materials to envelope, when we say envelope, now we are talking about walls, roof, and floors. So for that, we will look at the energy performance of those wall systems and also the durability aspect of those systems. For example, here we are looking at a modeling of sandwich panel, concrete sandwich panel. So normally we build concrete as single materials, but what if we put insulation? And where should we put the insulation? In the inside or on the outside or in between, which will give us high performance. So we'll be looking at that kind of examinations. Or it could be a window. Is it better to have high windows like that, or is it better to have shorter height and a longer width window, which will have an impact on terms of the thermal comfort and the energy. So this is kind of research we do with respect to building envelope performance. And the next one is, okay, now we do materials. We understand a little bit of materials, and then we do it as an envelope, as a wall. Then we can look at from the whole building perspective. So integration of the walls, and then we can have the mechanical system inside, and then we can simulate people's occupying and living in there in terms of their moisture generation, CO2 generations, and heat generations. Then we can look at the thermal comfort, how comfortable is that environment. So in this kind of you might have seen this test facility. They are in the southeast of our campus. So we call them whole building performance research laboratories. So this research facility would give us a comparative performance of different systems, of different operations. Right now, we are also working on building integrated photovoltaic thermal systems. So that's to enhance the integration of the PV system into the building. So not as standalone kind of component, but as a part of the building envelope. And can we actually enhance by increasing, for example, the heat transfer or the flow, the air transfer? Can we actually extract some heat and use it for the HVAC or for the building performance? So these are the general areas from materials to envelope, whole building, and new technology. These are the areas that we do in our centers. But now I'll be just shortly tell you, we don't have much time, but I'll just give you kind of an example of a project that we do. This is also a test facility at the southeast part of the campus. Our facility, we call it a building envelope test facility, a 2-story building, 48 feet by 28 feet. And you can see panels, 4 feet by 8 feet panels. I don't know if you can see them like this. So all of the panels that can be interchangeable. So we can have different designs or materials put side by side, and we can evaluate their performance given the exposure to the same in outdoor environment climate conditions and the same indoor climate conditions. So we can have a comparative study. So I'll be presenting some results from this test facility. As we know, this is a North American map. As we know, our region is actually a very, very wet region. We have over 60 inches of water or rainfall, so which makes it very difficult for buildings to perform. So we have to have additional measures or design to make sure that actually the buildings could get wet, but they should be able to dry out. In addition to high rain, the solar radiation is not that much. So the drying potential is also very low. So it makes it challenging. So we have a lot of waiting rain, but you have less solar radiation. That's the combination of that could be a very difficult or problematic. And this is like a leaky condo crisis. So when you have a combination of design, materials, and loads, and then if it's not properly designed, then you will have a significant problems. So this is due to rain leakage at the wall window interface, and the other picture is due to condensation. So like if you not control your indoor humidity, like in the bathrooms or in a residential house, and if you have some openings that moisture will be going through the envelope, it will condense, and then it will rot it. And you will not have any way to know it, actually. That's a big problem, especially when you buy a house and so on. You have no idea what the enclosure looks like. So we have to come up with some kind of designs to control rain load from the outside and also moisture flow from the inside to the outside and create condensation, create a problem. So in this test, we will be looking at 3 test panels. The one, I think, let's see.
The laser pointers won't show up on the screen.
No? Okay. Okay. Is that right? Okay. So, okay. So here we have three designs. The one on the right, the dot lines. Okay. Okay. The dot lines are called vapor control. That means vapor inside the house, not to migrate and condense on the sheeting, the plywood or the exterior. This would be a vapor control. And here, this is a cladding, which is kind of a stucco or whatever material you have on the exterior. In this case, it is attached to the plywood. In this case, we have, again, the vapor control from the inside, but here we have created a gap between the cladding, the exterior sheet stucco or whatever cladding material, and the sheeting material. So we have some air gap. And here we have air cavity, but we remove the vapor barrier. So we try to see the significant impact of these designs on this wall performance. So typically we instrument the panels. This is the top plate, bottom plate, and these are the studs and the sheeting. So we'll have measuring sensors at a different location of the sheeting and also on the stud. Typically temperature, relative humidity, moisture content, pressure, and anemometer for airflow measurement at a different section of the wall. Here you can see also in the insulation, inside the insulation. Based on this experimental design, we put our sensors, and then we wrap it up. We put the insulation, and we make it just like as it's built, and then we will install it in our test facility and connect it to terminal strips, and then finally to our data acquisition system. So we measure weather every minute. Every minute we take reading of temperature, relative humidity, solar radiations, wind directions, and so on, every minute. And the walls response every 5 minutes. We measure outside local conditions and measure inside condition. And this here also you see a wind rain. So we know how much actual rain actually takes hitting that wall. And we have here a panometer. We know the solar radiation that these panels are getting. So we basically characterize the local boundary condition that these walls are exposed to on the outside and also in the inside. So this would be a fair comparison how these systems perform. So this is a result, a comparison of if we have gap or not. Actually, we didn't have a gap for a long time. Now in our practice, there is a gap. It's called a rain screen wall. here, the one at the bottom here, the pink line, you see the solar radiation, and the black one you see rain. So here, as you have more rain here, solar radiation actual magnitude is less, which will be the moisture content. This is the moisture content on the plywood, on the sheeting. It increases. In the summertime, it goes down. And this is the deviation, the impact of having the air gap between the cladding and the sheeting. So by having the gap, you're actually effectively reducing the impact of rain coming here, wetting the cladding, it could be a stucco, and transferring to the inside. So that actual gap makes a huge difference. And this is a comparison of if you have a vapor barrier. So we talked about we can have a control inside a vapor barrier and air gap for the outside. So this is a case when you have a vapor barrier here in the inside. That's a polyethylene sheet, like just behind the drywall. Or if you don't. As you can see, it is very significant. Like it could go up to 22%. That means you might probably have a mold or a significant durability problems. This is done in Vancouver climate, which is kind of mild climate. Imagine if it's done in Ottawa or Toronto or Winnipeg, very cold climate. This would be dramatic. So this shows the very importance of having a vapor control layers. And this is just to show, like, in our test facility, the southeast orientation, or in our climate actually, in Vancouver area, we get a lot of rain in the southeast orientation. So southeast orientation is called a predominant wind and rain direction. You get a lot of rain. So in the northwest, you will have less. So what kind of performance do you expect? A wall in the northwest, which is less wind and rain, and the wall on the southeast, which is higher. So here you clearly see a change, a difference. It may not be that significant, but still there is a change, a better performance in the northwest wall. So when you design a wall, you might choose to have pressure-treated plywood, for example, on the southeast orientation, where you have a lot of, you expect a lot of problem, and less on the northwest wall because your load is significantly less. Then you can have a regular kind of system. This is just a comparison of, okay, those two control mechanisms, like if you have a vapor barrier or if you don't have air gap. As you can see here, even in our climate, even if we have a lot of rain and rain is dominant, actually the vapor control is very important. So if somebody say, oh, the weather is mild, we don't need a vapor control, that's not true. Actually, it's very, very important, even in our climate. So in conclusion, with no vapor barrier, the moisture could be as 2 times as with a vapor barrier if you have a system. If you have a gap, actually you can significantly reduce your moisture load on the sheeting, which is called a capillary break. Basically, you are breaking the moisture diffusion from one layer to the next one, because air cannot hold a lot of moisture. It will not be actively transmitted. But if the two materials are close, then it can have it directly transmitted. So that's effectively doing. Yeah, we get higher moisture accumulation in the waiting season, and then we can have highly drying in the summertime. But the most important parameter here is how long do you get that waiting period, and for how much and for how long. That depends on your mold growth and decay, that kind of parameters. So this is a measurement for 1 year. So if you extend it, then you might have an incremental moisture accumulation. If you compare the vapor barrier and wind and rain loads, definitely still in our climate, vapor barrier is important, and also it could be significant. I think that's it, and I'd like to acknowledge the support from INSERC, CRC, CFI, BCKDF, industry partners, and my school. Thank you. Any questions?
What do you plan on developing next?
Right now, we are working on sustainable building materials using hemp, for example, hemp fibers. So we are in developing stage in developing materials, and also we are actively working on integration of building integrated photovoltaic system into buildings. I think that would be very important.
Good. Thank you very much.
You're welcome.